Okay, so now we would like to get get ahead with the next overview. Remember, we have not actually gone into the modalities per se. So we first kind of did a quick review on 2D signals and systems, and now what we would like to do is get this hang of image quality. What do we mean by that? So far what we have talked about is a medical imaging systems course. The imaging system, the overarching objective of an imaging system is to capture the inherent 3D distribution of some parameter and display a output. So the output estimate should be as close as possible to the underlying 3D distribution of the body with respect to mostly structural and functional aspect of the physiology, right? So now the question is, okay, so what is important? We need to study about the system. So when we have to study about the system, we already talked about system impulse response, right? Kind of helps us characterize the system. But notice, what is the overall objective is to see inside the body for what? What is the purpose? The purpose is for the doctors, right, the physician practitioners, the radiologists, to essentially use the information they get about the body when they see what is there inside, right, through the medical imaging system. The output that you get, right, the medical images, they have to make diagnosis, right, they have to make, based on that they have to take some decisions. Do they see an abnormal growth? Is it normal? Is it abnormal? Is it even if it is abnormal, is it severe or is it early stage, right? So they can and which part of the body, which organ is having a problem. So all this they need to take out, infer, right? So the importance of medical imaging system, even though from an engineering perspective we will feel happy to see how this is transforming a 3D distribution into an output image, the mathematics of it or the instrumentation of it or the physics of it, the real purpose, the real benefit of this imaging system is for clinical practice, right? And therefore now comes the question, so how do we want to argue about the image quality? The actual image quality, when we talk about, does it allow the doctors to make, is the quality sufficient, is the image reliable for them to make some judgment, right? That's, so we need to have some benchmark. So we need to know, if they say, okay, I am not able to infer from this, we should be able to know whether is it underlying, that's the best you can get, or there is a problem in the instrumentation, or there is a problem in the signal processing, or the problem in the display screen, right? All this how will you do? So that means you need to be able to assess the image quality, right? When we talk about assess the image quality, we need to assess the image quality mostly from our perspective, mostly from how does this imaging system capture the inherent dynamics of the distribution, inherent ranges that are present in the 3D, right, on the input side. Is it able to faithfully, truthfully capture that much, right? So we should have some tools to understand and assess this based on the imaging system. So clearly this is a more, I would say, being a coursework kind of lecture, I had to really try to be complete, at the same time give a big picture view. But the moment we say image quality, I know you all know examples, right? What do we mean by image quality? Oh, image quality, we know some of the metrics, right? When you buy a cell phone, we always use this cell phone as an example because you may have a very good feel for it, right? When you buy it, you will say, oh, this gives a very good quality image. You would have used these terms. You will say, oh, this gives good resolution. I can see different colors. I can see, I took this photo of a butterfly and I can see some colors that are appearing very real, right? So, you get the best contrast, right? I see even very high signal to noise image quality, when you start, you say see very little, less noise, right? You would have used these terms. In fact, some of the things like you would have also used, you would have seen deblurring, motion deblurring, right, options in your, so you get these cameras in your cell phones that come with automatic deblurring. So you would have inherently you probably have a feel for what is image quality and what are some of the terminologies or metrics that are used for it. So what we will do here is kind of give a overview of what is the more structured organization of these terms, right? What does it capture? What does it mean? How do we use mathematics to describe this? It's going to be very modality agnostic, meaning in this we will not really jump into any particular modality. We will try to capture these terms, terminologies and the meaning of it here. When we get into individual modalities, which I said will be self-contained, there we will contextualize these image quality metrics as to whether it is from the physics, whether it is from the instrumentation, specific physics, specific instrumentation, right? All those things we will do. So here it is going to be a kind of a modality agnostic terminologies and concepts. Okay, so it's going to be very quick overview, very touch and go, like this is the concept, this is what you probably heard before, this is what we will try to do. Okay, that is how it is going to be covered. So much for introduction. So now I have said the answer. So what are the image quality metrics that comes to your mind? Resolution, contrast, right? Those two probably come. Noise, less noise, signal to noise ratio if you are a little more careful, right? What else can you attribute? Artifacts, right? Is there anything else that comes to your mind when we talk about image quality, right? If at least you are able to recall so much, I think you are in a good shape. Okay. So contrast, resolution, noise, artifact. There is this distortions. So that we will get. So we will try to establish what these mean, and then when we go to modality specific, then each of these metrics we will again view it. Okay, so distortion. So there is a subtle difference between noise, artifacts, distortions. Subtle difference as in there is a difference. That's why these are all different things. But unless you make note of the minute difference, all of them may seem under the same basket. This is all corrupting the image so that the doctor is not able to see a feature he wants to see, for example, right? So we'll go one metric at a time now. Okay, so let's start with the contrast. Just before we jump into it, again I mentioned it. There are two aspects to it. Broadly, we are interested in two aspects when we talk about image quality, right? All the metrics that we saw, some of them are basically coming from physics oriented issues. What do we mean by that is that there is an imaging system that produces an image output, and we talked about the metrics, right? Contrast, resolution. So these image quality metrics are affected, right? The image quality metrics capture the effect of different physics oriented issues, right? So as an engineer, as a medical imaging system, say signal processing or instrumentation or biomedical engineer, you will be interested, you will be very comfortable in understanding the image quality from the perspective of how does the system perform in truly capturing accurately the underlying 3D distribution. That might be your forte. So image quality is important, is captured for that reason, right? All the contrast, signal to noise ratio, artifact that we talked about, all of that. But there is also some task oriented issues. What do we mean by task oriented issues? Now task is what? Here biomedical doctor. So he needs to find out whether there is a abnormal growth or not, right? So his interest is not in whether you report a full width half maximum to be 2.7 mm plus or minus 0.3, and our new algorithm, processing technique improves it by 5%, right? That may get you a paper, right? But then what is the doctor interested? The doctor is interested in knowing whether there is a tumor there or not, whether he can confidently, reliably say that this is a tumor and measure the tumor, and then do prognosis. Say, okay, if this is small, you can come back after 6 months. If this is greater than this threshold, you have to right away schedule a emergency surgery. So he has to be able to make all these judgments. So his image quality is not about only your objective metrics. So my contrast is minus 3.77 dB better. So that's fine, but the image quality from a task oriented issues, you cannot capture it like that. You may have to capture it using different metrics. So the contrast, resolution, noise, distortion, all this will be used. We will understand what it is. All this will be used to understand the imaging system, how well imaging system does, right? So that is our major interest. However, we will also just highlight this issue so that you are receptive. All these are connected, okay? Because if you do a good imaging system which is able to capture the underlying distribution well, then the question comes whether it is clinically useful. So the doctor wants to use that imaging modality to make some diagnosis, right? So he is more interested in sensitivity of the system, imaging system, or the specificity of the imaging system, diagnostic accuracy of the imaging system. That is what he is more interested in, right? So there are two broad aspects. So understanding this image quality is very important. Not just understanding, objectively be able to come up with the models so that we can tease out where the image quality, if you want to increase the image quality, we need to understand what are the factors that are contributing and work towards that. Or if this is the best, then the doctors have to get trained to make use of the modality. So it's important from either perspective that you see. Okay, so let's move on. The first image quality metric that we would like to understand is contrast. So when I say contrast, what comes to your mind? How do you know this? You've been using it in different contexts. So contrast means, what does it broadly try to, the sense of what it conveys is, there is a difference. Contrast means something is different. Different from what? Something I am looking at is different from the surrounding. That's how you contrast out. His idea was in contrast to somebody else, right? You use this in a different colloquial terms, but each of the time when you carefully analyze, you use this word to capture or make sense of how do you say one from the other. How do you tease apart one from the other? The target from the background. That is the context, right? So to put it in our perspective, we will say difference between image intensities of an object of interest to the surrounding object or background, right? Very good. So it kind of not, it is not too far away from what our colloquial use was. It's just that we have changed it or made it little more specific to calling it as image intensities, that is different, of the object of interest and the surrounding. Okay, so this is good with English. How do we capture it? See, if you want to do any understanding, analysis and compare, you need to have some mathematical language, not English language, right? Mathematical language. So how do we capture it, right? Why is that important? The importance is because I am going to show you an image which we saw already. So qualitatively, using this English descriptive language, we may be able to appreciate it, but in order to jump in and really make a mathematical statement of it, and then that can be used subsequently, because different modalities are there. So we should have some quantitative way to do it, right? So qualitatively you may appreciate, right, this is the same image that we saw earlier. Why did I put it here? Now we will have to look at it from the contrast perspective. You quickly recognize that For example, each modality has its own ability to contrast out the target from background. So, I have to define what is a target, I have to define what is a background. See, that is a, but when you look at the overall image, right, this is a CT scan of your head, this is MRI, the second is MRI, third is PET. Quickly you will see each one is different, but the contrast in PET, right, especially of the regions, right, you see a blue region and yellow. So, there is a good contrast, even though it is color. I mean, even if you convert it to grayscale, one will be more towards white, the other will be more towards black or grayish, right. So, you will see that this region is well contrasted out compared to, for example, the corresponding regions here. If you compare this with the surrounding, right, if you compare this with the surrounding, clearly this region to this region, it is all the same gray level, right, it is all the same gray level. Whereas, if I take the same region here, oh, I can say, I can clearly see that as different regions, right. So, that means the contrast is inherently high in PET. So, what do we mean by all this? Oh, image intensities of an object of interest, surrounding objects or background, right, that is what the difference between them is what is captured. So, clearly depending on the modality there is a fundamental, see we did not really go in depth, which we will, but we know here we are talking about radioactivity as the signal, here we are talking about the nuclear magnetic resonance of your hydrogen, here we are talking about attenuation coefficient of the tissue to your X-ray energy, right. These are the inherent signals. So, what this tells is some modality there is a inherent contrast is better than the others, the capturing the inherent contrast is better than the others. Okay. So, okay, it is fine, but how do I now say this mathematically, how do I put some equations and then use that metric and kind of capture this qualitative assessment? Can we come up with that? Can we have a quantitative metric that captures what we qualitatively observed, right? So, for that we would like to introduce the idea of modulation. Modulation means, modulate means usually variation, right, you modulate it means you vary, it is not at the same level. So, here what do we mean by modulation? Oh, I have signal should not be at, so when do you contrast? Oh, I have to have some intensities in the target, some other intensity in the background. Only if these two are different, there is a question of contrast come into picture, right. So, that means how different these should be. Oh, is there a more structured way of creating different intensities in the image? It can be modulate the signal. So, the idea of modulation is how do we get different intensities in the image. If we get different intensities in the image, then the idea of contrast, we can then pick which one to contrast from, which is our target, which is our background, or we want to talk about local, global, how do we want, all that we can go on. So, modulation from what we know already, right, can you think about some signals that can be used for this purpose, right. So, this is something that I would like for you to think right now. Did you see any image so far, any signal so far? I gave a clue, we saw an image. So, any signal so far where you could think about the signal is changing in intensity, right, in an organized way. I mean, the previous slide also we saw intensities were different, but it's very difficult. It's a human brain with inherent intensities of various pattern. Did we come across any signal where the intensities were varying, but that we can write mathematically, right? Think about it. Keep that in mind. Maybe it will strike a bell once you read this. So, we are going to identify modulation of a function, right. We are going to capture the modulation in the function, right. You have a signal, we want to capture the modulation in the signal, that means it is varying. So, we want to capture this variation. How do? We can do it several ways, but one of the easier way to do is capture this modulation through modulation function as f max minus f min by f max plus f min. What does that mean? It essentially means, contrast we talked about difference, right. So, f max minus f min means 2 intensity difference, right. F max plus f min means, so you can think about it as amplitude, right, amplitude difference f max minus f min, or okay, divided by the average. Okay. So, difference by average, that is going to be your contrast, right. So, that means if I have an image, if I have an image signal, so in that image if I have intensities that are changing, how do I capture the modulation in that image, so that I can capture the contrast, right. Oh, I need to take contrast is difference. So, I can take amplitude difference f max minus f min by f max plus f min. Okay. So, this is on the whole, if I give a function f of x comma y, I can capture the modulation in the function by this. If I capture the modulation, you get some sense that already contrast definition was difference between 2 intensities compared to the surrounding or background. So, you can start to think that this modulation, if you capture this has to do with contrast. Okay. So, that means can we cleverly define a signal where we could capture this modulation. From what we have done so far, you should be able to recognize f of x y is a function. We used sinusoids, right, vertical bar at an angle, remember that is your intensity. There was a black, white, black, we spent some time on that, capturing the frequency of oscillations, right. So, that is a test signal where the intensity is varying in a known fashion, known as in mathematically you can write it as a sinusoid at certain frequency. Of course, just for simplicity we have used only one variation, f of x comma y is only having x. We know how to write in y also, right. So, when we showed the examples of u naught and v naught, right, it is the same, it is a signal where the intensity is varying in one direction or the other, or it can be at a slant. So, it can varies in both the direction. Just for simplicity we are taking a sinusoid at one frequency. So, now you understand, if this is a test signal where the intensities are varying, how do I capture the contrast in this? First we can understand what is modulation function. So, from this, what is the modulation function for this? Oh, go by the definition, f max minus f min by f max plus f min. So, maximum is sinusoid is 1, minimum is sinusoid is minus 1. Okay. So, you can already think about reducing this to f max and f min is going to be determined by the sinusoids plus 1 or minus 1 value, and then you have a and b. So, you can get right. So, you can essentially get modulation function to be b by a. So, this is your modulation function. Okay. How much the background, right, how much the difference is standing out, how much your target is standing out from the background. Here we did not specifically talk about one particular target. I mean, of course, we are taking the difference, the maximum difference, f max minus f min is the maximum variation. So, that is a maximum contrast you are looking at. So, that is what we have captured here, b by a. Okay. So far so good, right, but this is not sufficient. Why? Because our interest is not just, okay, this is a good concept to use, model, this captures some underlying, I mean we can capture the contrast idea in this, but our interest is not just that, our interest is how does the imaging system perform, right. So, what does, just before we go to the next question, just to have some visual representation and understanding, MF equal to 0, what does that mean? Oh, B by A is 0, okay, MF is 0 means difference is 0, the numerator is 0, okay. that means f max is same as f min, there is no variation. So, there is no variation, you see the image, oh, all of them are the same value, right. So, if mf equal to 0 means the modulation function is 0, that means there is no modulation. If there is no modulation, you are not going to have contrast. Whereas, if I have mf is equal to 0.2 or 0.5 or equal to 1, you slowly but steadily appreciate, oh, the right, the values are becoming, so here the contrast is very high. So, there is a region where there is a thick black that dies down to grey, and then there is a white, right. I can say, I can see the bars much better. So, this is having a higher contrast. So, clearly this qualitative impression of the last one being a better contrast compared to this one is also captured by mf. So, mf is always, right, 0 to 1 here in this proposition. We have taken f min can be non-negative, right. If that is the case, then you can actually get a sense that this is from 0 to 1, 1 being the best possible contrast, 0 being no contrast. Okay. Okay, so we understand that this mf can be used to capture the contrast. Now, what is our interest? Our interest is imaging system. So, I have an inherent contrast. So, I can present the input with maximum contrast, for example. My interest in the system is, can it preserve, can it transfer that, can it show the output image which the doctor is going to use? Does it have, that is how much of contrast is there in that image. So, there is an input, there is a system, there is an output. So, this test signal, the mf, is definitely good to capture the sense of underlying contrast variation. Now, we would like to see how much of this contrast that goes into the imaging system comes out. Can we use this mf idea to understand about what is the contrast in the output image when the contrast is, a certain contrast is sent into the input image, input data. So, what does the system do to this contrast? Ideally, you would have the system to pass whatever inherent contrast is there, it should pass it on to the output image, because that is where the doctor is going to be using it. Okay. So, let us take a imaging system, a simplified imaging system, LSI, linear shift invariant system. So, you are presenting it with the input, same input that we just saw, the modulation function. So, now I know my input, right, which is a very well defined function, for which I know my m suffix f. I can calculate the inherent modulation that is there. Okay. So, now we want to understand what will be your output modulation. So, if you send this through the system, if it is LSI, by this time you should be able to write down the output. This is f of x comma y. Use the variable h for your system. To get output, we will write in terms of g of x comma y, right. Can you write down what will be the output when you pass this input through a LSI imaging system? We did this last class, right. Linear systems theory, convolution in time domain or product in frequency domain. We talked about Fourier transform, transfer function, right. We already see some frequency here. So, transfer function, remember how much of the input frequency is captured, the Fourier transform we did. So, it, right, in the frequency domain, right, we can tease the signal out, decompose it in terms of its frequency composition. So, now I am presenting u naught, so it is a frequency input. How do I write the output g of x comma y, right. So, I can use my transfer function. So, I can write g of x y, a is some amplitude with 0 frequency. So, the response of the system at 0 comma 0 and your response of the system to u naught comma 0. So, you have only x direction frequency, right. So, your B is your amplitude, and then the system, how does it transfer the frequency content of u naught in the x direction, right. Capital H is your transfer function of your system. Okay. So, if this is the case, I have my f of x y, I have my g of x comma y. What is now of interest to us? Oh, we are not just interested in writing this equation. This we know from the signals and systems linear theory that we studied. Our interest now is to see how does the contrast in the input come out in the output. That means my m suffix f I know, right. What is m suffix g? Write down what is m suffix g. You know m suffix f, right. We did that in the previous slide. B by A. What is your m suffix g? Same definition. Maximum, right, f max minus f min by f max plus f min. Here g max minus g min by g max plus g min. What is the value? Can you write? Okay. G max is this guy, because sign will be maximum, and g min will be, sign will be -1. So, straightforward. So, now our interest is getting m suffix g. M suffix g turns out to be, if you do the g max minus g min by g max plus g min, m suffix g will come out to be like this. Immediately here you can recognize B by A from previous slide, we know is from the input m suffix f. Now you see there is a output m suffix g, modulation in the output is nothing but modulation in the input times something to do with the system response, correct. Clearly whatever the system response is, you can observe even here your output is also going to be sinusoidal. So, the input fluctuation was sinusoidal, the output is also sinusoidal, no issues about that, correct. But the contrast that is there in the fluctuation in the oscillations in the input, is it preserved in the output? Well, it is preserved depending on the system's response, right. Typically you do not get this to be 1. So, your mg will usually be less than your mf, clear. So, mg will be usually less than your mf. So, even though they are having the same oscillation, same frequency, right, the contrast in the output image can be, from this can be inferred to be less than what you will be at the input, because of the properties of the system. Okay. So, in that way we can define your modulation transfer function. Transfer function you know. Now, we are talking about modulation transfer function. What does it mean? There is an inherent modulation m suffix f in the input side. The modulation at the output side is m suffix g. How much of this modulation is transferred from the input side to the output side? That is your modulation transfer function. Of course, it is dependent on the frequency. So, modulation transfer function depends on the frequency. So, it is a function of frequency is equal to your mg by mf or this guy, right. So, now if you want to talk about the contrast that you see on the image that the doctor is going to use, you can clearly tell there is a influence of the system. So, there is a inherent, so if there is no inherent variation, then no matter which system you are going to use, you are not going to see anything in the output, right. If this shirt is of the same color, right now it is of the same color, right. No matter what, if this entire shirt is the same color, whether the pocket is there or not, you will not be able to make out, right. If I inherently I change, so if I keep a pen, this pointer here which is of a different color, now suddenly that is the inherent contrast, the camera can capture and say, oh, maybe there is something, so he is keeping his pen there. If there is no pen, right, if the whole shirt is the same color, the pocket is also of the same color. There is no inherent contrast, no matter which imaging system I am going to use. I am not going to see a pocket if it is well done. Maybe there are shadows or other things you can make out, but the point is inherent contrast is important. Okay. So, if there is inherent contrast, does this image, so if I keep a pen here, right, and you do not see anything, then there is a problem in the imaging system. Okay. So, the idea of this modulation transfer function is, if there is a contrast in the input side, does it come out on the imaging, the image that is going to be used in the practice, right. How does it capture, how does the system transfer this input inherent contrast to the output, that is what this is useful. So, let us take a example. So, we can clearly talk about this modulation transfer function, right, is a quantifies the degradation of contrast as a function of spatial frequency. That is what we saw, right. So, typically, like I said, it is going to be between 0 and 1. So, 0 and 1, so this is 0 frequency. What is 0 frequency? DC, there is no oscillation, so there is no contrast. So, if there is no inherent contrast, right, that you present in, the output will also be no contrast. So, that may, you can say the system is transferred, there is no, there is no loss in contrast. Why? Oh, there was no contrast in the first place that you sent through the system, so nothing to lose. So, you get the maximum throughput. Okay. So, MTF of 0, so typically your MTF at any given frequency is going to be in between 0 and 1. We saw this already, right, not MTF, we saw the modulation function, what happens if it is from 0 to 1. If that goes in, your output also has the similar pattern, but then how much is transferred is captured by MTF. Okay. So, how do we do this? Let us take a example case, right. So, this is what is a plot of a MTF. So, we talked about MTF being a function of frequency. So, frequency in our context is going to be spatial frequency. We have taken the variation in x direction as to be a spatial frequency. So, spatial frequency is denoted by inverse of length scale, remember. So, spatial frequency versus MTF is plotted. So, you start out at 1, there is no variation, DC value, you get maximum transfer, and then as the frequency increases, this drops down. So, what does it say? It looks very similar to, you would have known this, right, very similar to your, okay, as a low pass filter, right. So, this is frequency, this is the response. So, after a certain point, right, oh, here for example, after 0.6, so if the frequency of that oscillation, that black to white to black to white to black, right, the oscillations in the thing, if it gets faster than 0.6 millimeter inverse, already I see drop of 50% of the value. That means whatever was the maximum value, that, right, maximum minimum we are subtracting to get the contrast. You can already tell the MTF is only 50.5. So, that means the contrast has dropped, and when you move further after 0.8, so if there is a variation in this black to white to white to black, if the variation is more than 0.1 per millimeter, then I do not get any modulation at the output. So, if I send my input has a frequency that is greater than 0.8, right, the output I will not have the f of x comma y can, if it has greater than 0.8, the output g of x comma y is not going to have anything, there is not going to be that oscillation that you see, right. So, this is very important. That means, what would you desire this MTF to be? The MTF should be, oh, you want it to be all pass, right. Why? Because the higher frequencies, remember we did one example case of, just to get this idea of frequency that we did, we had a sagittal view of your head, right, and then we had the spectrum. This was when we did the 2D Fourier transform, and I showed you the example as to how you can make sense in the spatial domain as this is the head, nose, brain, whereas in the spectrum you have a bright spot at the center 0, 0, and then you have, it's just scattered all over the place. Recall that what did we do there? Oh, we tried to reduce the higher frequency through the higher frequencies, and then there was an effect in the image. What was that effect? We talked about blurriness, right? Remember, recall. So here is similar. If I increase my frequency more, then the contrast is going down. That means the fluctuations are coming down. The oscillations, I don't see it. So in fact, after a certain point, I don't see. So I might give a oscillatory input, but my output is going to be a DC value, 0 value, from a contrast modulation function point of view, right? So there is a relationship. So ideally you would like this MTF to be as high as possible for as many frequencies as possible, because that's when you see greater detail. That's what we talked about earlier. Okay, so that means this can be used, this MTF can be used to study the different imaging systems, correct? Or even within the imaging system, you can change various parameters and see its effect on the image quality in terms of contrast. So for example, an imaging system is given and following MTF characteristics is what is obtained. So we say, oh, this is imaging system 1, this is imaging system 2, this is imaging system 3. Let's make it simple. All of them are the same modality, all of them are otherwise very similar. It's operating on the same, it's capturing the same target image, but this is the response you get from the 3 system configurations. Then what would you infer? What would you comment on this? Well, going by what we discussed, all of them are having high value at 0, right? So okay, all of them are equally good if you want to send an image where there is no oscillations, a homogeneous image. All of them will perform well. But if you look at the other interpretation, oh, this is frequency and this is falling off, I would like to have as high a value as possible for as much frequency as possible. That is my best case scenario. So if you look at it here clearly, oh, this is broad, this is wide here, narrow, narrower, and it falls down, it still has some value here, whereas the corresponding location, say if you take the second line here, right, it is MTF is some value, whereas if I take the second line here, the MTF is clearly lower than this value. If I take the second one, it's already 0. So that means there is no transfer happening at earlier frequencies itself. So you would expect that this is higher contrast, this will provide higher contrast compared to this, So this is in some decreasing order of contrast capability of that system. So if you look at it in the image, right, so decreasing contrast, if you look at it the image, what is the effect of that, right? So we present the same input, but the 3 different systems configuration is here. This is the output that you see. What is the effect? Oh, decrease in contrast. When we say decrease in contrast, you look at it, not just decrease, oh, you can understand, oh, this is decrease in contrast, MTF is low, and I can qualitatively say that, oh, this is of better quality than this, and this is the poorest amongst the 3. And the fluctuation between white and black, right, what we are capturing here is for all frequencies, right. So on the whole, the image, if you look, this has a better contrast than this, right. But what you should recognize also is, when the frequency, higher frequency content reduced, the image starts to look blurry. This is something that we saw with the head scan as well. So there is going to be some relationship between your resolution and contrast. But here you can clearly appreciate using MTF. If the MTF is falling off like this, right? How does it capture the image contrast quality of the image global, right? I just said the contrast of this image, this is global. So, this captures the contrast transfer ability of the imaging system. So, when you give an image input or inherent contrast distribution, how much of it comes through at the output, that is what this MTF is capturing. So, you can extend this, right, you can extend this to arbitrary frequency. I mean, just use the u, but this can also be written h of u comma v instead of just the example that we took. So, the very handy thing we will work about when we get to each of the modality, we will try to put meaning to that capital H, right? What is it? What is the physics? How does that H get affected because of the physics of the modality, and therefore, how does the contrast get affected because of the physics of the modality or the instrumentation of the modality, right, or the signal processing aspect of the modality. We will go one at a time when we get to independent modalities, individual modalities. Okay. So, that is good, that is for global contrast, but sometimes we may not be, not all the time we are just looking at engineering perspective and say, oh, we got a good, I have calibrated the system, this system has the best MTF. That might be true at a global scale, but the doctor is probably not interested in the global view of it. He is interested in actually looking at a particular location where he wants to see if there is a tumor growth at an early stage, or how much has it grown, right, or can he demarcate where it is ending, so that he can go into a surgery and remove that. So, the interest is not global imaging system, the characteristics. Can he have a local contrast? Can he see the target that he wants to see? How well can he see it corresponding to the immediate background? He is not interested in seeing in the same frame different objects with different contrast. He is interested in looking at a particular object in its surrounding neighborhood. So, he is not interested in putting all the dynamic range into one image. Okay, he wants to see local target. So, then what do we do? So, then we can essentially use the same thing. You have for simplicity it is plotted through x, the same concept you can extend it to y. So, you have a image intensities. So, you can take that function, you have a target value and a background value. So, what is the contrast? Oh, contrast is going to be difference between how much this stands out compared to the background, how much the intensity in the target stands out compared to the background, that is your local, right. So, how was, so here you can say this is, so intuitively speaking, if I want to do, say if I can see whether this stands out compared to the background, it is easier if Ft is much larger than Fp. If Ft comes smaller and smaller, right, smaller and smaller at one location, probably the difference between Ft and Fb is not much. So, it is not standing out. So, in some sense the contrast is poor, it is very difficult to spot where is the target, what is the background. So, inherently contrast, we talked about difference between the intensities in the target and background. If that is already high, that is inherently high, that is good, but then your imaging system should transfer that. So, imaging system cannot take the black one as the input and give an output G of B and G of T, for example, that has a profile like this, right. So, if the input is F and G is your output in red color, if your MTF is such that it takes the black and produces the red, it is a very poor imaging system, because the doctor now has to differentiate the small difference. He has to make sure, oh, this is the target, this is the background, based on the small difference between target and background. So, it might not be that obvious to reliable. Okay. So, that means you can calculate your local contrast as Ft minus Fb by Fv, just normalizing, right. So, Ft minus Fb by Fb. So, this again we will end up using, this is again depends on the context, okay, depending on the context one metric over the other can be used. So, if you are dealing with something specific you want to, then your local contrast might come into a rescue. You may want to use this to capture that. If you are just interested in the characterizing the system, then maybe MTF is a better tool. Okay. So, let us stop here, right, with contrast, but before we do this, I would like for you to do some thought exercise. I do not know how well it will come, because in class, in a live class, usually we sit in a classroom and I have the ability to switch on the light and switch off the light. Okay. So, what I am going to do now is I will try here, but perhaps you could try it at home also and convince yourself what is going to happen. So, the question is, what happens if constant intensity is added to all the pixels? So, I have an image f, right, and I have a contrast that I am exploiting, local target. There is a target, there is a background. What happens if constant intensity is added to all the pixels? Mathematically, I know you should do it, you will see, but intuitively what do you expect to happen, right? So, for example, I am going to try this, I do not know how well it is going to come. So, there is a and this is an assumption that because they are going to process this video and they are going to do some contrast enhancement, equalization, what not. So, maybe it does not come out that well. So, if you do not see much effect here, maybe you should try it on your own. So, notice that I have a contrast between my skin color and my shirt, right. So, this is my image of interest, f of xy is capturing this part. So, now the question is, what happens if I add constant intensity to all the pixels? What will happen to the contrast? Okay. So, I will just try and perhaps you can do it. So, what I am trying to do is trying to add intensities by having a torch. So, I am putting more light both in the background and target. Now, what happened to the contrast, right? I have captured the contrast as Ft minus Fb by Fb. My shirt is my target, background is my skin color. Okay. So, now if I add light, I am adding white light both in the target and in the background. What happens to the contrast? Okay. So, please think about it, try to do that and see whether you are able to appreciate how these metrics capture and what happens to the interpretation. Thank you.